All right, while Giorgio is setting up, I'd like to introduce him as our next speaker. Giorgio Serveri is a PhD student at Northeastern University in Brookline, Mass. And is completing or has completed recently a fellowship with FireEye, one of the premier data science teams in our industry. And he's got some interesting work to present to us today. As soon as he...
Yeah, let's make this work. Presenter view.
On exploring backdoor poisoning attacks against malware classifiers. So let's welcome Giorgio.
Thanks. I can talk in this? Can everybody hear me? Is that fine? Okay, perfect. Thank you very much for the introduction. So yeah, Giorgio, I am a PhD student at Northeastern. I was recently at FireEye for some time this summer. And today I would like to talk to you a little bit about some exploration work that we did on backdoor poisoning attacks for malware classification, right? Okay, so we are going to explore a little bit what happens when the attacker can get their malicious data inside our training pipelines, right? So we are in the setting of training a machine learning classifier, and it pretty much looks like this, right? And I really thought this picture would be like in 1,000 different slide decks today, but I was lucky. So we got the data coming in, a lot of linear algebra, and finally model comes out. And if we zoom in a little, it should essentially look like this, right? So our security Inc. company will take, of course, its proprietary data sets. And since it needs a ton of labeled samples, it will most probably rely on some external sample feeds, right? And those sample feeds can be things like services that provide labeling, where users can upload their own binaries, and so on. And the company would proceed doing some subsampling probably, will train their models, and in the end, if everything goes right, we will have a deployed model that will be able to classify correctly the malware binaries that are in the wild, right? Perfect. So now that we have our setting, let's take a huge step back and talk about what is backdoor poisoning, right? So most of you are familiar with the adversarial examples in the context of evasion. So like, for instance, think about your classic picture of the panda. You apply your adversarially crafted noise, and the panda, for magic reasons, becomes like a gibbon or a giraffe or whatever. And as I said, these are called evasion attacks. Now there is a different class of adversarial attacks, often called poisoning attacks. And those attacks shift the point of view, right? We are thinking about an attacker that has access to the training data, that can control in some way the training data, and the attacker goal here is to inject some characteristic in the final model. Okay. So we're going to talk about poisoning attacks, which is a very nice family of attacks introduced by Gu et al. In 2017. Very interesting paper called Bad Nets. If you haven't read it, it's a strong suggestion there. And actually, in this class of attacks, the attacker objective is to inject a watermark in the data points that the model will end up relying on this watermark to correctly classify the target class. And we're going to talk about actually a subclass of this class called clean label backdoor poisoning, introduced by Turner et al. In 2018, where we are not able to actually alter in any way the label of the data points. So we can just add noise or perturbations to the training data. And a quick example here would be if you take enough images over 7, or probably a 1, but whatever, 7, and you inject our perturbation in those images at training time, can you condition the model to predict 7 when you apply the same watermark to, for instance, a 0? So in the rest of the talk, you're going to hear me talking about vectors I know in security vectors are completely different things, but for the moment we are talking about this. Okay, so what are the research questions here that we are trying to address? Well, the first is the obvious one, right? What does a vector poisoning attack look like for malware classification? And the second one, slightly more complicated, does this actually work? Like, is the attack successful? And third one, really hard, how stealthy can this attack be, right? Are we going to be just detected on the fly, or can we make them stealthy? So if we go back to our schema over here, we see there is a natural injection point, right? Because the security company is going to rely on external feeds, and some malicious users can start disseminating watermarked goodware samples and leverage those external feeds in order to poison the data that the security company is going to use, right? And if everything goes right for the attacker, in this case, the attacker will have effectively backdoored the final model, right? And so at test, like later on when the model is deployed, the attacker can just introduce its watermark in the malware samples that the attacker releases in the wild, and hopefully the new vectored model will not be able to classify them correctly as malware. Great. But, okay, so we're not actually going to put purple pixels inside binaries because that would be really hard and probably would not work in this case. What exactly do we mean when we talk about watermark here? Watermark here is just a specific assignment of values to a selected subset of features that the trained model will use, right? So here you can see a random example. It doesn't really have anything to do, but it's just to show what the features are and what does it mean to assign a value, right? So for instance, you can see import a feature that is really the results of an hash function applied to the imports, some byte histograms, and we can assign values to those features. We should also talk a little bit about the attacker capabilities, right, our threat model. We have already said that the attacker has to be able to access the training data in some way, and we see there is another way to do that. But in this case, we are also in the white box scenario, right? So the attacker has complete knowledge of the model, and we can categorize the power of the attacker into these 4 nice categories. So the strongest attacker is an attacker that can modify every feature, assigning any value. Super powerful. And then restricting the subset of features and values that the attacker can modify, we can, model our attacker. Perfect. Okay. So what would the poison generation look like, right? This is probably, I don't know if you can all read this, but essentially we are in the white box scenario. We will use the training data and we will use the original model in order to select our subset of features that we want to attack and the subset of values that we want to assign to those features. Then we will pass these data points to our watermark applicator that will effectively inject the vector in the data points. And we will pass these watermarked samples to the model that will be trained, along with all the classic, all the clean data points, like all the clean, benign, and malicious data points. And hope that in the end we get a poison model. Okay, how did we test this? How did we experiment with this? I don't think I have to introduce the Amber dataset here. It's been talked about a lot. It's from Endgame or Elastic, and the important things here is that we have around 2,300. Yeah, sure.
Are you controlling the label also?
No, that's a clean label, so no label control here.
You're pushing
Yes.
whatever samples and they get, let's say it's virus, so it'll get scanned by.
Yes. Oh yeah, the question was if we were controlling the labels, and we are not. We are in a clean label scenario. Is that okay?
Clean labels
As in non-modified.
I mean, you're making a sample and you're submitting to the virus
Yeah.
point, it's out of your hand, but it's labeled.
Yeah, exactly. That's why we are not assuming that the attacker can actually modify the labels because it's out of our control.
But you're assuming they stay the same as the original?
Yeah, we are assuming that they stay the same for a moment. Okay, so as we can see, this is a list. This is of some subsamples of the features that are present in the Ember dataset. Some of them are the result of hash functions or counts of frequencies, and some of them are more, we can say, probably natural, like, I don't know, number of strings in the binary, has or not has debug, and so on. And another interesting thing that Ember did, that we can use about the Ember dataset is the released light GBM model, which was very useful for us. So, okay, perfect. So, where are we? We have to decide which feature to attack, right? And for the moment, our natural, like, let's say, our basic intuition is just attack the most important features, right? The features that contribute the most to the final classification. However, we wanted to find a model-agnostic way to do this, right? And there is a lot of work going on in model explainability in the latest couple of years. I am not an expert in model explainability by any means, but we can leverage the great work by Landberg in 2017, their SHAP technique, Shapley additive explanations, which essentially gives us the value of the contribution of each feature for each training point to the final classification value. And we will try to use this as essentially a way to determine our feature importance. So these are the strategies that we use to craft our watermark, right? As we said before, maximum importance is the natural strategy. Then we have these, we want to use these SHAP values, so we sum the absolute values of the SHAP values. And then we have two different ways to select our values to assign to those features. One is the minimum population, because we just want to try to find those values that make the watermark unique, and so make the model rely on it. And we also experimented with something that is slightly different, actually a lot different. We consider very common data points, very common values that, however, contribute less to the final classification output. And as you can imagine, we tried a lot of bunch more of these values and feature selection strategies, but these were the most promising. Okay, so which metrics are we interested in? As we said before, obviously, if it works, right? If the attacks succeed in changing the classification. Then we are also interested in the accuracy of the backdoor model on clean data. We want to know if our attack is degrading the ability of the model to generalize correctly on standard clean data. We're also interested in false positive rates because false positives are bad, and security companies care for false positives. So we don't want our final model to be to have huge spikes in false positives. And we are also interested, this is kind of tricky here, on the accuracy of the clean model, of a clean model, cleanly trained, on those goodware that we watermark. Okay. And we will see a little bit about it later on. But essentially, they are all defensive point of views, right? We want the attack to just not be noticeable. Okay, so I hope you can actually see the plots here. Is this better? Great. I hope you can actually see the plots. We can see here for 4 features and for 8 features what is the actual effect of our attack. You can see the baseline at 100 because we are only attacking malware points that were correctly classified as malware by the baseline standard clean model. And we can see that for 8 features, we actually, with our largest SHAP and our count plus SHAP strategies, we get around in the upper 99% attack success rate, with around 1% of the whole training data poisoned. And another interesting thing is that the attack actually improves with larger watermarks and more poison data. So from this, we can actually pretty much say that those SHAP values are actually working as a proxy for feature importance. Now again, we can look at the other metrics that we want to see, and this is probably too small, okay? But essentially, there is no concrete loss of accuracy on the known watermark, on the clean data. There is a small increase in false positives, but nothing too visible. And also a small change in the watermark that would wear accuracy, right? So in the accuracy of the clean model on the watermark data. I am probably going to go a little bit faster here, but okay. The obvious question here is this practical? Can you actually do it? And modifying any feature, assigning any value, is something that may not be possible, right? Either because the features are the results of hash functions, or because there could be undesirable interaction between the features. Now, the second one is really hard, and we are still working on that. But the first one, we are trying to address it right now, right? So we limit our attacker by allowing the attacker to modify only 35 features in the dataset that are not the direct consequence of a hash function. So this one that pretty much we saw before, the more natural ones. And we can see that actually the attacks are slightly less effective, but only slightly. For our reference, 8 features, 1% of the dataset poisoned, we get around 91% of attack success rate, which is pretty decent for this kind of attack. So the effectiveness is comparable, and the attack still improves the more features and the more data points you use. Again, as before, no particular loss in accuracy, maybe a little more with 4% of the dataset poisoned. Slightly more false positives, still nothing great, a little bit more than 0.1%, and a slightly larger change in the accuracy of the clean model on the watermark data, but again, in the ballpark of 1%. A final word about defenses. So we're not really going to go too deep about in the defensive analysis, because it's really evaluating defenses against adversarial machine learning is a really complex task. So we leave this for future work. But we also didn't want our attack to be trivially detectable, right? So we experimented a little with some basic defensive approaches, like using, for instance, isolation forests in order to see if there are anomalies in our incoming goodware. And we also tried to adapt the activation clustering defense. This comes from a paper by Chen et al. In 2018. This was a defensive technique that was proposed for neural networks on images. We tried to apply it on like GBM on malware. So there was some machinery going on there. But essentially, none of these two basic approaches seem to be working in really detecting the watermarked samples, right? We see that they essentially, the number of real watermark that they find and the number of just benign goodware that they find is pretty much the same in percentage. Okay, so last word on defenses. Where would we want to defend our pipeline if we were trying to defend it, right? So the first thing is defensive subsampling. If we had a way to do that, that would really be a problem for this attack. We tried, of course, our anomaly detection method that didn't work, but maybe some further research in this area could provide a concrete and final solution here. Then we also, as we said before, tried to measure against old model to see if there are any differences. And obviously, we want to monitor for false positives and false negatives spikes. Okay, what about limitations? So, as you probably have got it by now, a practical implementation of this attack is difficult, not impossible, but it takes effort because of the need to find modifiable combinations of features and values, right? The nice thing is that if we find relatively small but important for the model combinations of features, then that is probably sufficient to get a very good attack success rate. Again, we see that if we think of an adversary submitting millions of watermarked samples to various services online, this may raise alarms in some way, right? But we think that a sophisticated attacker that has enough time and resources to spend this can just spread the dissemination over time. And this should be enough to mask the effort. Subsampling may, even random subsampling may filter out large portions of the attack. But again, an attacker with enough resources can try to watermark very diverse set of goodware, of benign samples, and just evade this kind of thing. And finally, we tested on a single model, on a single dataset that is relatively small for the standards of the industry. So that is, for future work, we need to experiment more. Okay, takeaways. Untrusted, crowdsourced, labeled data sources are actually a vector of attack for poisoning attacks. We should start considering benign binaries as possible vectors of attacks, because we all know that malware is malicious, but also goodware can be malicious. And finally, we think that variance, so this diversity in the types of benign software benign binaries that we find, may work in favor of attackers trying to do this kind of poisoning attacks. Okay, thank you very much.
Thanks, Giorgio. We do have some time for questions. Sure.
That was really interesting. Thank you. The watermarks reminds me a little bit of data leakage, and I was wondering if there was a way of perhaps having an expert evaluate the results afterwards and look at what the most important, equivalent of most important pixels would be to see is the model picking up on actually the pixels that we want, or picking up on the watermark, the watermark in each case.
Okay, so the question is, can we get an expert to actually validate the values that the feature assume in the data points? Okay. Yeah, I think that would be possible, but you would probably have to pay an expert to do this job. So, yeah, it's probably possible. That is true.
I think, Giorgio, this is a super important topic. I think feeds in the malware industry can be extremely susceptible to poisoning. Do you have any comments, maybe from you or your team, about having observed any of that practice?
A real attack in the real world? No, I don't think we have observed it. I think this is mostly a theoretical exercise for the moment. But I also think that it is doable in practice. Like if you're an attacker that has enough resources and enough motivation, I think it could be possible. Yeah.
As I'm going on, I will note there was a time when Endgame noticed a precipitous drop in a feed, and we corroborated with another industry, actually competitor, but on a friendly level, and they saw it too. We thought maybe there was a poisoning attack, but it turned out it was a student competition uploading a bunch of stuff.
Hey, thanks. That was very interesting, and I'm just kind of like imagining different possible mitigation strategies. So I think possibly what the first question was maybe also getting at was the idea of using some of the work we saw earlier around like visualizing what a convolutional neural net is learning from a raw byte sequence. we saw that for those examples presented, there were certain parts of the binary that lit up in terms of identifying malware. In this case, I would expect that, like, if you were to look at a visualization for the watermarked things being labeled as goodware, because of the high variance you mentioned, real goodware should, like, not exhibit any kind of general pattern, I would think, intuitively, whereas watermarked things might have, like, some very specific area of the binary that's lighting it up, so that could be one possible mitigation strategy.
That sounds very interesting. Like looking for, instead of abnormal behaviors, looking for very normal behaviors.
Yeah, exactly.
That could be a very promising direction, yeah.
Hi, I wonder how much of this is dependent on you sort of indirectly controlling the distribution of benign-ware that vendor is training on, supposedly, right? And one easy mitigation for a fairly large vendor is to stop training on benign samples that are in VirusTotal and only train on the intersection between internal telemetry and VirusTotal, or in addition to its internal labeling of its internal telemetry. And how would that affect this method?
Yeah, that is a possibility if you're assuming that a powerful enough company can afford or has access to that kind of telemetry and information. I think that is a possible thing to do. But also, there is the fact that the company should be able to discriminate which are the watermark samples, right? Or just train on proprietary data. Like if the company has enough proprietary data that they are absolutely sure it's not compromised, then yes, sure, that is true. But if it has to rely on anything external, and there is no, like, for the moment, there is no way to telling the watermark from the non-watermarked, then it gets really hard.
Hi, I'm actually one of Giorgio's co-authors on this. I wanted to just respond to that quickly because he's a student at Northeastern, and we actually do the malware stuff on a daily basis. So yeah, I mean the answer is if you have enough internal goodware on your own, then come talk to me because I'd love to know who you are and how diverse your goodware is. The reality, right, is that you think about the universe of all things goodware can do, and you think about the universe of all behaviors that malware does, and like goodware is much, much larger, right, in terms of that space. So, getting a huge diversity is a difficult question, and I think it's a fair question what you're asking, but I also think it's practically very difficult to just completely exclude the possibility of using these crowdsourced data sources for goodware data set creation.
How does this work on trapdoors for goodware? How does that relate to recent work on non-negative weight models that specifically prohibit adding benign features to change modification? Because if the watermark is associated with goodware, then with non-negative weights, it should not be an issue, right?
Yeah, that is a good point. We should try that kind of evaluation. We didn't at the moment. We didn't even try on neural networks at the moment. But yeah, that is a very interesting question, and this is part of our future work, trying on different models. One of these include the non-negative one. Thank you.
Wonderful presentation, Giorgio. Let's give him one more round of applause.
Thank you.